Hello, in this video we'll be talking about the process of double replacement reactions, also known as metathesis reactions, and we'll be talking about them in the context of salts. So when you see the word salt, your first thought is probably of table salt, which is the stuff we put on our food. And that would be because table salt is an example of a salt. So what exactly is a salt? Well, a salt is just a generic term for any compound where an ionic bond is formed between a metal and a nonmetal. So you'll have a positively charged cation, metal bonded to a negatively charged nonmetal anion. And they're typically solid and crystalline at room temperature. So let's think of an example of a salt. So we just said table salt. Table salt is sodium chloride. So we'll take a positively charged sodium ion, Na+, and we'll bond it to a negatively charged anion, let's say chloride. And there we have sodium chloride. Sodium having a +1 charge, chloride having a -1 charge. So when you're making, or when you're drawing out the formulas for these salts, you'll want to keep in mind the charge. And so there's a way to look at this, and then there's another way to look at this. So the first way would be what is sometimes called the diagonal rule or the crisscross rule, to determine what your subscripts will look like for your salt. So if you were to use the diagonal rule, let's say we would do it for sodium chloride. So we'll take sodium ion, which has a +1 charge, and we'll take chloride ion, which has a -1 charge. And what we're going to do is, in the final product, in the salt, we're going to take the charge here and move it down next to the sodium. We're going to take the charge here and we're going to move it down next to the chloride. And what it'll end up looking like is, in a 1 Cl1. So see how I took the -1, not ignoring the charge, but paying attention to the number, taking that number and moving it next to the sodium, taking this number and moving it next to the chloride. So Na1, chloride 1. That means we have 1 sodium ion and 1 chloride ion, and that makes a neutral salt, and we want our salts to be neutral. So we want an overall charge of 0. We want the positive to cancel out with the negative. And that's another way you can think about this. So if we ignore sort of that diagonal rule, another way to look at this would be by thinking about it in terms of charge. So if we have a +1 charge on the sodium and there's a -1 charge on the chloride, they cancel each other out, so they make a neutral compound. And that's how you can think of it. You'll need how much of either cations or anions depending on what is needed to cancel out the charge. So let's take another example. Let's take calcium. So calcium has a +2 charge. It's in group 2. And let's say we wanted to bond calcium to chloride. So if we wanted a neutral salt containing both calcium and chloride, what would the charge on here tell us about how many chlorides we would need, given calcium is +2, chloride is -1. Well, if we wanted an overall charge of 0, we would need 2 chlorides. So our final product would be Ca Cl2, because we have 1 calcium, and typically when you only have 1 ion in a compound, we just don't write the 1, we just leave it. And then we have 2 chlorides because that equals a total of -2. It's -1 each, and for the calcium we have a +2 charge as an ion. So these two charges cancel each other out, and we're left with a neutral salt. Well, let's look at it from the other perspective too. Let's say we have sodium and we want to bond it with sulfate. So we want to make a salt with sodium and sulfate. Sodium has a +1 charge, sulfate has a -2 charge. So how many sodium ions would we need to cancel out that -2 charge of the sulfate? We would need 2, right? So that means we would bring a 2 down in front of the sodium. So our final product would look like Na2 SO4, because we have 1 sulfate ion with a -2 charge, and we have 2 sodium ions, each with a +1 charge, which gives you a total of +2. So the +2 and the -2 cancel each other out. And this is how you can predict what your salts will look like based on charge. So now let's move on to the actual idea of the double replacement reaction now that we've gotten that charge situation out of the way. So in this double replacement reaction, we're reacting 2 aqueous salts with each other. And if you remember from previously, we know that aqueous just means that both of these salts are suspended in a solution of water. So we'll take sodium chloride and we'll react it with potassium nitrate. And we're going to first predict our products. So in a double replacement reaction, it's called double replacement because things switch around for the products. And what I mean by that is that the sodium will switch to the nitrate. So the sodium will go to the nitrate, and the potassium will go to the chloride. So basically the ions swap places with each other. Another way you can think of it is that the metals swap place with each other. The cations swap places. And so your final product will look like this. So we'll have NaNO3 plus KCl. So all we've done is swap the Na and the K. They've traded places. So now the Na is bonded to the NO3 and the K is bonded to the Cl. And we know they're going to look like this because, as we talked about before, the charges will dictate what they look like. So sodium has a +1 charge, and nitrate has a -1 charge. So they cancel each other out. Same thing with potassium and chloride. The potassium ion has a +1 charge, and the chloride ion has a -1 charge. So they cancel each other out. So that is the gist of the double replacement reaction. In the next video, we'll talk about solubility and how to predict if your double replacement reaction produces a precipitate, which is a solid.